Hello and welcome to this edition of 30 Mechanical Minutes, virtual content for real-time professionals. My name is Doug Picklyk. I'm the editor of HPAC Magazine, and the topic for today's session is optimizing boiler chemistry. I'm joined here today by regular HPAC contributor Steve Goldie, along with Brian Morgan from the Morgan Group. Hello, gentlemen, and welcome.
Hey, Doug. Thanks for having us.
Thanks for being here. First, I'm going to start with a little background on my guests. Steve, he's been a longtime writer for HPAC. He's also the hydronics specialist with Next Supply here in Toronto. A plumber by trade, Steve joined the wholesale side of the business after 21 years in the field. Brian is a principal with the Morgan Group, an experienced manufacturer's representative focused on commercial heating and residential HVAC solutions, including a large variety of products for the hydronics industry. Between our two guests, we have many years of on-site experience visiting mechanical rooms of all shapes and sizes. So if you have any questions during this session today, please type them into the questions panel and we'll try to get to all of them before we sign off in about half an hour from now. Okay, Steve, I'm starting with you. I was saying when I think about my hydronic system that I have running in my house, it's attached to the municipal water line. So the fluid in my system is city water. Is that not optimal?
Well, as you said in your introduction there, Doug, I've been around for a while. I'm 21 years of contract and almost 20 years in wholesale. So I hate to say I've been in this business almost 40 years. And you know, when I started out, and you know, for most of my, all of my career installing boilers, water was what we used. That was the optimal medium. It's a great heat transfer medium, and it's cheap and it's available. And we never had issues. And in the old days, the most important water treatment device that we had was our air separator, because the biggest issue in our system was not the water, it was the air. And when I do trainings, I always tell people, I always ask people, what causes rust? What rusts steel pipe? Oh, what happens when you put it out in the pipe yard? It rusts up when it gets wet. Well, how come I can have a 80-year-old house with a boiler and rads and steel pipe filled with water and it doesn't rust? Well, because water doesn't cause rust. What's rust? Rust is oxidation. So it's the oxygen, the air in water that causes rust. So when I was growing up, we had cast iron boilers, cast iron rads, copper piping, steel piping, and water chemistry wasn't something we thought about. The best, when you got the air out, so like I say, the most important water treatment device was your air separator. Once you got rid of air, oxygen, you didn't have an issue. And the water in the old systems was like this black, smelly, dead, inert water. And we used to say, well, that was, we used to call it black gold. A system filled with that black, dead, stagnant water, that was great for a heating guy. That was great stuff, because you weren't, that meant you didn't have air and you weren't going to have issues with oxidation and rust. And so treating water and checking chemistry and water chemistry wasn't an issue, because the old boilers didn't really have a lot of issues. Cast iron boiler, copper fin boiler back in those days had large passageways. They didn't have small passageways, so they weren't prone to getting plugged up or sediment plugging them up. And I did mostly residential in those days. It wasn't really an issue. It's a much different ball game today. The boilers have changed, systems have changed, and I would not be shocked to find out that the water has changed in some ways. I always thought of city water as being soft, like Toronto city water was treated water, and it wasn't particularly hard water. It wasn't on the hard water spectrum. But I think Brian might refute that. I think he's got some water test results that might say something otherwise. And you can see, as the graphic you brought up there shows some of the calcium and the hard water issues in piping and waterways right there. Brian?
So I think one of the things, Steve, just to go along with that, when we look at how the industry has changed and boilers have changed, a big part of it is the heat exchange. And as you can see, these are great pictures. And on the left, you see a cutaway of a cast iron heat exchanger, a high mass boiler with a lot of water volume. So as it does scale, there's a lot of opportunity for scale to build up. The newer technologies, and I don't care if we're talking about copper heat exchangers, stainless steel heat exchangers, aluminum heat exchangers, a lot of the new technology, whether we're talking residential or commercial, are much smaller passageway. And the great news is it creates hot water really, really quick. The bad news is it creates hot water really, really quick, and that's where we run into some problems. So that comment about a municipal system, I just got a report back that we were looking at where most boiler manufacturers will recommend anywhere less than 150 parts per million or less on what you're seeing in your water. Here I've got a municipal system, and this report I just got back is over 210 parts per million when you're looking at water hardness. So, there is an issue even at the municipal level when you're looking at water chemistry and what you might be putting into these new hot rod boilers that we're using for condensing purposes.
Right. Now, I look at that picture on the left there. That's a cutaway of a cast iron section. That's the kind of boiler I put in, hundreds of those, and they would last for, some of them could last 100 years. Like really, they'd last 30, 40, 50 years without a problem. And they probably lasted with scale like that built up in them. But the passageways and the water volume was huge. So if you had a bunch of scale in the bottom, most of the heat transfer is, I'm pointing at that, thinking I'm pointing, but you can't see where I'm pointing. But the little heat, the knobs on the outside of the heat exchanger, which catch the heat, they're still could absorb a lot of heat into that water. And you're still going to get a lot of heat transfer, and you're not going to have an issue with that boiler. But like you say, the new boilers have a lot of surface area crammed into a very small package, and so that means the water volume is a much smaller volume, and the passageways are much smaller. Stainless steel, which is probably the most common heat exchanger material these days in condensing boilers, is not nearly as good at heat transfer material as cast iron or copper. So you need thinner walls, you need smaller passageways to transfer the heat fast. They do transfer heat very, very fast. And here's a picture of a fire tube, down-fired fire tube or water tube boiler. Fire tube boiler. And you can see a lot of scale in that boiler. And that, in this particular picture, all of that, the burner would be on top of that, at the top of this heat exchanger. So the highest concentration of heat is where all that scale buildup is. And so the scale buildup is creating an insulation around the heat exchanger, preventing that transfer of heat, which will cause that heat exchanger to overheat and in time fail. Like I say, in the old days, we could have a cast iron boiler that could be full of sediment, and it wouldn't fail for years and years, if ever. But the new boilers, they will fail and they will cause a problem. So water chemistry is critical nowadays. Where, like I say, back in my day, the most important water treatment component was your air separator. Now, that's not the case. We want to test our water. We want to make sure that the pH is good. We want to make sure that the hardness is in line. If it's too hard, we're probably going to want to, either put. I know that a lot of places they'll actually order water. They got a water truck with pure, not pure water, but soft water that's not. It's not got a lot of hardness in it, not a lot of mineral in it. If you're hooking up to a municipal system, you can fill up your system through a cartridge or a system that will take the hardness out before it goes into the system. I'm a big fan of those. They're relatively new, but I'm a big fan of those demineralizing cartridges that you can attach either initially when you're filling it up, and you would purchase them based on the size of your system to do X amount of gallons, or you can put one on that's actually got a meter on there that will tell you when the water starts getting too hard. It will trigger an alarm to say, look, we need to change the cartridge, or you're going to have a problem.
Well, this kind of makes me think about Brian, from a boiler manufacturer's point of view. What are they recommending for optimal closed loop performance when you're designing or setting up your system, whether it's new or retrofit?
So we pulled some information from some different boiler manufacturers, and everyone in a roundabout way talks about chemistry that you're using within the boiler system. They look at things like pH, they look at things such as the hardness of the water and the mineralization of the water. And when you go back and you look at that picture that you showed of that fire tube heat exchanger, what will happen is if you have a lot of minerals in the water, you're causing that burner to be very, very hot in touch with that heat exchanger, and that's where you're going to get the solids coming out of the water. So that's when that tends to happen, and that's why you're starting to see things like this. So every single boiler manufacturer has something that talks about water chemistry and the importance of it. And they do make a number of different recommendations that you should be looking at when you're installing their equipment. And some are even going so far that it will potentially void their warranty for what they will have on their actual heat exchangers. And that's one of the things that I think a lot of boiler manufacturers are really coming back on, because as Steve said, years ago, this was never an issue. Started introducing this newer technology for condensing boilers, these issues start to pop up and these boilers aren't lasting as long. And now as we become more informed, we're like, hey, these are some of the things that are really, really important. What you brought up right now from warranty considerations, this is from one manufacturer's manual that I saw, and they put in some best practices that you should be looking at for your boiler system. And some of the things we brought up already, they're saying test the water before you're filling it. Make sure you have air elimination in your system so you don't get that oxygen right in the system. Treat all your boiler feed water and make sure that it's not hard water. Use chemical inhibitors on every job, not every once in a while, but on every job. Flush old and new system before commissioning the boiler. Use the magnetic dirt separator. Use dirt separators to remove debris from the system water. And where possible, always treat that water. So there's a few things that sort of come into play here. And, if you have an existing commercial building and you have all that copper or steel piping that's been corroding for years and you're putting in a new boiler system, typically a lot of the times in the older buildings, those boilers are in the basement. So you put in this new great piece of condensing equipment, and next thing you know, in a couple of years, you have a major issue in your hands because all that sediment is coming and resting in the boiler. And sometimes it's very difficult to flush the entire system, or the contractor's worried about flushing the entire system, so they just valve it off, replace the boilers, and they're on their way. But there's a couple of different ways you can do this. You can test the water, treat the water before introducing it to the boilers. Another thing you can do as well, you can also look at decoupling your new boiler system from the existing system with a heat exchanger. And then that way you're ensuring you've got great water quality going through that investment of those boilers. So that's one way you can do it. And then the other thing too, the age-old adage was always just hook it up to the water feed system going into the building. But as we've seen, even through a municipal system, the quality of that water may not be good. And if there is a leak in that system, more and more and more oxygen, minerals, and things will be deposited into that heating system. So another practice we're starting to see as well is actually completely decoupling your hydronic system from a backwater feed system and using a makeup package. And by using that makeup package, you're able to, one, treat your water and test it very easily. You're also able to see if you do have any leaks in your system, which should be causing bigger problems throughout the system as well. So these are some of the scenarios on what you can do to ensure that that new condensing boiler package is going to operate at its peak performance for a long time for your customer.
I want to go back to what Brian was saying. He covered a lot of points there, and you also, Doug, you said we're talking about. I just want to clarify. We're talking about closed loop systems, and what a closed loop system is a system is closed from atmosphere, and it's closed off typically from the water supply. You may be connected to water supply through a makeup water valve, but ideally you fill the system up. Once it's filled, you're not putting fresh water in there anymore. And as long as that water has been, like Brian talked about, as long as it's relatively soft, its pH is balanced, and all of those things, it's good water. You get the air out, and for years and years you should have no problem. But the problem is we can't guarantee that anymore. We can't ensure that we have none of those issues. And if we're doing a retrofit, like Brian said, and we've got a lot of stuff in that system, including microscopic, fine metallic, particulate that can build up and become magnetite, which is why we'll talk about magnetic filters are very, very important, because that's something that builds up, and I think you've got some graphics to show that. But it's very important to go back to that. Can you bring up the picture of the boiler with the calcium in it?
The
fire tube
condensing boiler or
That's
the
the condensing boiler.
I think is what Steve is referring to.
Because I just want to clarify, that's a cutaway of a fire tube boiler, which is a very popular design, an excellent design in a closed loop system. But I want to make the point, a lot of the water tube stainless steel condensing boilers that we have a water tube design that can be used for either closed loop heating boilers as well as open loop domestic hot water boilers. Same heat exchanger. This type of heat exchanger, the fire tube heat exchanger, you'll never see being used as a open system domestic boiler. And that's because the high concentration of heat at the top of that heat exchanger and then the surface area is very, very prone to that hard water, calcifying and building up like we see here. So that type of design is never going to be used in a domestic water boiler. In a closed loop system, in theory, we shouldn't have that problem. But as you see here, we've got a problem, and that could be caused by any number of things. If that water line that fills your system, your makeup water valve, is connected to your city water service, and you have a small leak in your system, and over time you're continually feeding new fresh water in there, well, you're putting new fresh calcium and minerals, which are going to end up caking that heat exchanger just like that. And I've seen closed loop heating boilers that have been installed in buildings where they've had leaks that in a very short order of time will fail because of this. The other thing I'm seeing in a large commercial building, your water has a certain amount of minerals per million parts. And in a soft water system, you might have, like you showed the manual there that says what the acceptable level of hardness is. Well, you could install a boiler in a building and you can test the city water and say, okay, city water is fine. It's within those limits. You think you're fine. The problem is there might be so much volume in that building that there's still enough over time, there's enough mineral content in that volume of water, even though the water itself is within acceptable limits. The total volume brings so much calcium into these heat exchangers that you're still going to have a problem. And I've seen that happen as well. So that's where I'm a big fan of. Brian mentioned isolating your boiler system from your building. So putting a heat exchanger in between the boilers and your system, that enables you to have a much better control over the boiler water quality. If you put a brand new boiler system in a retrofit building and you've got you take all the care in the world and you fill up that system, you flush your system, you fill it up with decalcified water, you test your water, your pH is good, everything's good, you flush it all out, you think you're good. Well, you've still got this massive building. Now the boiler installer puts it in, he certifies everything's good, off you go. Well, 6 months down the road, the service contractor comes in and he's got to replace a rad valve. And to do that, there's no shut-off valves, so he may have to drain the whole building, or he may have to drain an entire riser. So he drains an entire riser, which could be a couple hundred gallons of water, drains that down, does his repair, fills it up again. Well, what's he filling it up with? Is he filling that up with that decalcified water? Is he putting it through a demineralizing cartridge? Probably not. Does he even know about the boiler system? And he may not. So if this happens once, twice in the season, over the course of a couple seasons, you've got service contractors coming in, draining and filling, draining and filling. Well, over a very short order of time, you can bring in enough water into that system that you're going to cause bigger issues. And again, I've seen this happen. So for me, especially if you're using a particular type of boiler that's prone to it, isolating the boiler room gives you much better control. Now that service contractor can come in and he can drain and fill that system on the building side till the cows come home. My boiler side is going to have a much smaller volume of water, much more isolated, system of water, much more easier to control that quality of that water and maintain the quality of that water over time and monitor the quality of that water over time. So premise isolation, as we call it through heat exchanger, is often done when you've got a building so high that you have to protect the boilers from high pressure. Well, I see that this is a very advantageous thing to do, not just where you have pressure issues, but now to maintain water quality over the long term. And it may seem like, well, a lot of unnecessary expense to add heat exchangers and pumps, but that expense up front is going to save you a whole lot of money down the road and a whole lot of pain down the road. Again, I've seen this as experience talking. I've seen this happen.
Yeah. Brian, I wanted to ask you about the use of glycol in systems. We know for snowmelt situations, it's a necessity. I just wonder if you can, how does that affect systems, and what's the, I guess, best use of glycol when you're using it in your hydronic system?
So there's a couple things. I mean, obviously glycol, the main thing, as you indicated, is you're looking for freeze protection. And when you look at most homes, you're not really concerned about freeze protection because you never expect them to go below freezing. However, sometimes there are isolated events where things do happen, like we did have it here in Ontario, the major ice storm, and there was a lot of damage caused by hydronic systems freezing, which, you know, glycol could have helped with that. But the other thing, when you look at glycol, there's two things I think you get in it as well. Number one, all the glycol manufacturers actually include inhibitors. And in those inhibitors, they're making sure that there's things to lubricate the seals, lubricate your pumps, and a lot of good things that really help your hydronic system overall. The second thing, though, you're also getting out of that as well is if you buy a pre-mixed solution, they have done that with neutral treated water as well. So therefore, when you are adding that into your system, if you are buying a pre-mix, then you're set because you've got a good chemistry going into your hydronic system. If you buy a pail that's 100% and go right to that municipal water or that well water, you're contaminating what that opportunity is there, and it should still be tested. So, you know, when you look at glycol, it's more than just freeze protection, which is still a good thing to have, but it also gives you inhibitors, and then it also gives you a good neutral selection for your chemistry for that hydronic system as well.
Right. Okay. And I mean, we kind of touched on isolating your system. Steve, you mentioned, I mean, in the case of a building, but also perhaps isolating the system from the municipal feed, or if you have well water and
Right.
you know, keeping your boiler clean that way.
Well, yeah. So using when you have glycol in the system, you typically will have a glycol feeder, and your system won't be connected to the municipal line at all. It's going to be connected to a reservoir tank that's going to have a particular volume of glycol or mixed glycol and water in there. With a pressure switch, and it's going to maintain the pressure in the system at whatever fill pressure you need, rather than having a pressure reducing valve connected to your water line and a backflow preventer. Again, in the old days, I would have never thought of doing that in my house. But now, if I was doing a hydronic system in my house now, I would not have it connected to the municipal system. I would have, whether I had glycol or not, I would want a glycol feeder, because that's going to ensure that, if I do have a leak or a problem, and you may not have a leak. Sometimes we have, if your expansion tank's not sized properly, or if your expansion tank is ruptured and not working, you could have a relief valve that blows off on a regular basis. Now, if you've piped your release valve to a funnel drain in a boiler room, you could have a relief valve that goes off regularly and nobody knew about it. It's just dumping water or glycol down the drain, and then the makeup water filter. Because if you've got a makeup water valve connected, as you lose water, your system automatically replenishes water. Well, that could go on for months or years, and the building owner wouldn't even know in theory. So if that happens, I don't want to find out that happened, because, oh my brand new boiler I just spent a lot of money on, my high efficiency boiler, is now scrap metal because I didn't realize we had this expansion tank that wasn't working. I was dumping water down the drain and new water's coming in, and lo and behold, boom, I've got 2 years down the road, I got to replace my boilers again. And oops, manufacturer had a look at it, saw that the heat exchanger was all calcified. They're not honoring the warranty because they don't warrant open systems, which in effect is what this has been installed in now. It's been open because you keep putting fresh water in it. So, you know, it's having a glycol feeder would solve that problem. If I have a leak or my relief valve's going off, my tanks, my reservoir is going to get, you know, empty pretty quickly, and the alarm's going to go off. Or if it doesn't have an alarm, I'm going to, hey, whoa, my system's got no pressure. What's going on here? I got to look further and find out, hey, how come I'm losing water? Is it my relief valve? Do I have a leak? What's going on? I saw a building not long ago where it was an older building. They put a brand new condensing boiler in there, and there was one of the boiler lines was actually a steel line that was buried to go from one wing of the building to the other. Well, that line had a leak in it because it had corroded. And we found out because I think it was about 14 months after the boiler was installed, the boilers failed because the boiler failed because it had calcified and overheated and leaked. And the building owner was very upset to find out that it wasn't going to be covered in warranty. And the really sad thing was the building owner knew that he had a leak. He said, "Oh yeah, that pipe's been leaking for years." He knew that it leaked, but he didn't think it was a problem. He said, "Well, you know, we're always just topping up the water." He thought that was okay, and didn't understand again water chemistry and how these boilers worked. And unfortunately, that boiler failed, and he did not get warranty on that boiler because it was installed in an open system. There's a closed system that acted like an open system.
Okay.
So
Guys, we have a number of questions coming in.
Okay.
And we want to keep this to around half an hour. So I'm going to start firing a couple of the questions at you guys, if that's all right.
Sure, Doug. The only thing I didn't want to talk more about Magnetite at all.
Yeah.
Oh, yeah. You know, that was the one thing we didn't really, I mean, we touched on it. I guess it was really from the, within some of the boiler manufacturers that came up. Is that right, Brian?
Absolutely.
Yeah, and I'll make this quick so we can take some of the questions. But you know, Magnetite is basically what Steve used to call the black gold. Is not really gold anymore unless we're mining it. And the way to mine that black gold is through putting in magnetic filtration. And the reason why that's important is because with all these older systems and even the newer systems, there are metal particulates that are in there that we call magnetite. And what's happening is they're attaching themselves to, in this case, an ECM circulator. In other cases, it's the inside of the heat exchangers, which affects the actual heat transfer within a boiler or in a plate and frame heat exchanger commercially as well, or in an ECM pump. And if it's not properly managed, it's going to stick to that equipment and it's not going to perform at its optimum and it's going to fail. So we're starting to see this being put into manuals for circulating companies, boilers, heat exchanger guys to look at a way of treating it. And you know, as Steve said, just to go on the feeder side of it, whether we're talking residentially or commercially, feeders start as small as 4 gallons and run up to over 100 gallons. So it can work on either type of system. You can do that.
Yeah.
You can put in your filter, as you can see. Here's a residential filter on a boiler replacement, and you can see the amount of magnetite it's actually pulled out of it. So you know, when you put magnetic filtration in, you want to put it on the inlets to the equipment, so that way you're capturing it before it goes through the heat exchanger and actually ends up inside the heat exchanger, inside your pumps and everything like that. So this is one of the things where we're going to see more and more information from boiler manufacturers and pump manufacturers about the need for magnetic filtration. So yeah. I just thought we should make sure
if you're putting a boiler, if you're installing a boiler, a high efficiency boiler, and I don't care whose it is, on any retrofit system where you've got older rads, older piping, to me it's absolutely mandatory that you put a magnetic filter on that, on the inlet side of the boiler. Is absolutely crucial.
Yeah. It's becoming the norm, not the exception anymore.
It should be. Let's hope it does, because if it doesn't, we're going to have a lot of failed boilers down the road.
Okay. Thank you, Brian. Thanks for bringing up that part of the talk. Okay, here we go. Andrew asks, how do TDS, I guess total dissolved solids, affect dissimilar types of metals and corrosion in a boiler system? Yeah.
You know, I don't think the dissimilar metals is an issue. The issue is they will, the dissolved solids, just like in your kettle, if you're heating up the hot surfaces, the hot metal surfaces are like magnets to those dissolved solids, and that's where the calcium dissolved solids are going to solidify and build up on the surface of the hottest surfaces. So like in your kettle, your electric element, you boil your kettle a few times and you look inside and is full of scale. Well, that's what the inside of the boilers looks like if you got continued heating and fresh water coming into it. So I don't think the dissimilar metal is not an issue.
The only thing I would add to that, though, Steve, with a lot of the piping systems that are out there, you may have plastics or different types of metals. And, when we look at where the solids actually come out of the water, it's usually where there's a high temperature. So I think it's more of where that's actually occurring, and that's where you're going to see the solids actually coming out of the actual liquid. and that's going to be the bigger portion of where you're going to see it versus the similar metals. But if you do have some of the newer systems that are using different types of piping materials, there may be only smaller components where it's going to come out because there's not as much metallic in there. But it's usually the metallics where you see a lot of the actual solids coming out of the water.
Yeah.
Okay, someone, Craig, typed in, suggest turning off the freshwater feed system if the boiler system has a LWCO.
The water cutoff?
Low water cutoff. Yeah, I mean, the low water cutoff is a safety device. And, if there's a problem with the boiler, then that will shut the boiler down. But the one thing that this doesn't do is it doesn't necessarily change the initial issue that we're talking about, which is looking at the chemistry of that water. The next service guy that comes in may say, oh, the low water cutoff went out. Maybe there's an airlock. Maybe there's a leak in the system. Fill it with the city water, municipal water, whatever you're using again, and it's back up and running. But if there's a bigger problem going on within that system, that's not going to stop it. I'd say that's a Band-Aid solution, but it's not actually a full resolution to the system for the hydronics.
No, I think it's a good, when we talk about having not connected to city service, have a glycol makeup, you'll know if you've got a leak. Well, this is another way of knowing you have a leak. If you shut that valve off and you have a leak or your relief valve's blowing off, you're going to know about it because your system pressure is going to drop. So it's not a bad suggestion, but I expect if that's the case, as soon as that pressure drops, the first thing the building owner or someone's going to do is, oh, this valve's off. They're going to turn it on, turn it back on, and walk away, and they think it's fine, but that's probably not fine. So, not a bad idea, but it may not fix your problem.
Okay. Can you give some examples of certain areas in a boiler system where you might get air infiltration into the system over time?
Well, air, if your system is a closed loop system, the boiler is not going to suck in air. Where you can suck in air is at air vents. So that's the ironic thing. Like, we put in air vents to get rid of air, and an air vent is not an air separator. An air vent basically lets the air out where there is air. An air separator will actually, get rid of the micro bubbles of air and the absorbed air in water. So a lot of people will put air vents at the top of a system. So again, going commercially, at the top of your risers, people put automatic air vents. I hate that. I hate to see that. I tell people all the time, don't put an automatic air vent at the top of a riser. Why? Because the lowest pressure point in the system is the top of the riser. And if your pressure gets low, that air vent can become an air inlet port. So you can suck air in at an air vent is in the high part of the system. I'd rather see a manual air vent up there or just a valve, so that when you're filling the system initially, you can let all that air out, but then you need to have an air separator to get rid of the absorbed air. The air vent at the top of the system, to me, is just going to cause you more headaches and more problems. If you don't have a leak in the system, you shouldn't have any air entry points other than possibly an air vent, vacuum breaker, that kind of thing can become a reverse and let air in. But again, where air comes in is if you got an old style expansion tank, the non-bladder style, well, that's just a big tank full of air, and that traps that air. And over time, your tank is waterlogged. Well, how does it get waterlogged? Well, because over time, the water will absorb the air from the tank and it carries it through the system. So if you've got an old style open expansion tank, that's also going to be an entry point for air. That's where air will get in. So the fix for that, use a bladder style expansion tank. So if you got a system with bladder style expansion tanks and you have air vents in proper, in correct places, and you don't have automatic air vents sucking in air, you shouldn't have any entry points for air at all.
The other thing too, I would just add to that is when we're talking about oxygen, we're also talking at the molecular level as well. So, one of the things too, where you can sometimes get it is if an improper piping system was used, say, on a plastic system that is not have an oxygen barrier in it, you can still get oxygen diffusion through the wall of the pipe. And we've seen that from time to time where, ferrous components such as cast iron pumps and expansion tanks will fail prematurely because you've got oxygen diffusion happening through something within the system, whether it's an air cushion tank or whether it's a water potable approved PEX piping that might be using where they put that in for the inflow system when it should have been something with an oxygen barrier on it as well.
Yeah. Someone's asking, what about the lifespan of glycol? Chemical companies tell you it should be exchanged every 5 years because it loses its luster. Is that true, or just a chemical company selling chemicals? Gentlemen?
I would, do you want to go, Goldie, or do you want me to answer that?
Yeah, I think that there's two types of glycol. No, there's lots of different types of glycol, I guess, but basically it was propylene glycol and it was ethylene glycol. Ethylene glycol is less stable. It's toxic, and in my opinion, it should never ever be used in any hydronic system. Ethylene glycol does have to be changed. It's the type of glycol we put in our car batteries, in our cars, not batteries, in our radiators in our cars. Ethylene glycol, to me, never put it in your system. It's cheaper, but you will have to replace it. So in the long run, it's not cheaper. And when you have to replace it, you're not supposed to put it down the drain because it's toxic. You need to get rid of it through a hazardous waste depot. That's going to cost you money. It's going to cost you time. Do people do that? I know that people put it down drains, which is a big, big no-no, and you'll get huge fines if you get caught. So it's not cheaper. In my mind, the best thing to do is never use ethylene glycol. Use a propylene glycol, a food-grade glycol. It's non-toxic. It is more stable and will last longer without needing to be replaced. And if you ever do need to replace it or flush it, you can put it down the drain. So to me, it's a no-brainer. You know, no ethylene bad, propylene good.
I mean, just to add to that as well about the breakdown of the product, I mean, the breakdown is going to depend on a number of different factors, such as temperatures and other things going on in the system. But,
Yeah.
you know, I will say this, there's a lot of great suppliers of glycol out there that are more than happy to test what's in a system as well. So, I mean, to sit there and say you got to do it every 5 years, I would say what I would recommend is make it something that you test. Maybe it's every other year, just to make sure you're getting the freeze protection that you want or the inhibitors that you want in the system. And there's a lot of different places you can get that stuff tested, and some of the manufacturers will do it for free, and then you'll understand if you need to do anything or not. But it could last for years, well beyond 5 years.
Absolutely beyond 5 years.
Okay, well, someone else is asking, are there any drawbacks to glycol use when it comes to wear and tear on system components, for example, rubber gaskets and seals?
So, you know, I think a lot of the different glycol manufacturers, they're add inhibitors to it. Usually, I think a lot of those inhibitors actually enhance the seals and make them last longer rather than hurting them, but it will depend on the inhibitors that are in there. But I know a lot of those inhibitors, they do things to protect the system. The one thing that I have heard from time to time on wear and tear is that with glycol being a little more viscous than water, it's harder to pump it through the system, which therefore means you may need larger pumps, and you may need, you know, more heat capacity, because the specific capacity of glycol to absorb heat out of a boiler is different than it would be from water. However, when you look at a lot of glycol manufacturers right now, they have tables and things that you can look at. So that isn't as true as it once used to be, just based on the way of the different inhibitors and the different glycols that are out there now, where it doesn't have as much wear and tear on your actual pumps, and it doesn't have as much impact on oversizing your systems and your boiler systems to make sure you're getting the heat transfer requirement that you need for that system.
Yeah, and it's, you know, I'll say one thing too on that. As long as you're keeping your glycol levels down, you know, again in Toronto, I like to see 30, 35%, maybe 40 at the most. You don't really need more than that for most applications. A lot, you know, engineers, I know some of them are out there, they drive me crazy. They automatically spec 50% everywhere. It's just 50% is too much most of the time. And when you start getting higher concentration of glycol, that's when you're going to run into issues with heat transfer and pumping capacity sometimes. If you're sizing it and you know, putting the right kind of glycol into the right levels, the impact is minimal at best. So it's to me it's insignificant, but it can be an issue if you let your glycol get out of hand, as I'll call it that.
Well, on that, someone else has asked, what's your point of view about glycol foaming and causing heat exchanger failures, and then what causes glycol to foam?
So you can look at different manufacturers that will add an anti-foaming agent to the glycol, but I have heard scenarios where if that is not a part of the glycol that you are using, basically what they're talking about is when you have that turbulence within that liquid, you can actually get air bubbles that collect on the top of a heat exchanger, which over time would definitely cause damage to that heat exchanger or piece of equipment. But a lot of the manufacturers out there now on the glycol side do add an anti-foaming agent, and if they don't, even some of the boiler manufacturers, I know commercially, I've seen it in some of their installation manuals, where they actually make a recommendation on an agent to use to ensure that you're not getting foaming buildup within a system.
And I think sometimes if you're getting a foaming issue, you may want to look at your pumps may be oversized as well. If you're over pumping, you could be causing an issue, and that's a separate issue. But it's the glycol may help sort of expose that problem more than water would.
Yeah, we have a comment from one of our watchers saying, watch the pH of the glycol. When it drops, it attacks all the materials, overheating and dirty systems.
Again, like we spoke of earlier, pH is something that that's critical. It's, again, certain materials react more. If you've got aluminum in your system, aluminum is very, very sensitive to pH, so it's critical. But even with all of the boilers now, checking your pH and monitoring your pH is just should be a part of routine maintenance now. Checking your water, testing it, and making sure the pH is in line, your inhibitors are balanced and in line, and your water quality. That's the whole point of this webinar, is to emphasize water quality and chemistry is something you can't ignore anymore. You could ignore it once upon a time. You can't ignore it now. It needs to be a part of the regular maintenance schedule and routine of your boiler system.
Yeah, thanks, Steve. Brian, I'm going to come to you if you have any final comments to make, because we're going to wrap up.
I would just say this. I mean, as Steve said, when we're looking at boiler chemistry, I mean, a lot of the times the boiler manufacturers will say they're always the ones to blame because they're the most expensive piece of equipment in the whole thing. But the reality of it is, it's what you're putting through that equipment. And that's why you got to really look at what you're doing from a boiler chemistry standpoint. So when we look at some best practices moving forward, that would include things like always testing your water, using a cleaner, using an inhibitor or a glycol. Okay, those are your options on what you can be using for that bloodline you're going to flow through these systems. Look at magnetic filtration. That can't be ignored anymore. You want to make sure you're getting that magnetite and everything out of that system to protect your boilers and your pumps and your heat exchangers. Look at the option, now that you have to put in backwater feed valves onto all boiler systems, maybe a feeder makes more sense. Maybe it's more cost effective. It'll help you diagnose system issues down the road, but also make it easier to test the actual water quality that's going into that system as well. So, HPAC, I really appreciate you putting this together on boiler chemistry, because it's a very hot topic. And I think we're going to see more and more in the installation manuals of different pieces of equipment in a hydronic system, that it should be properly managed by the installer. And I would really like to encourage everyone, give the owners the understanding as to why this needs to be done. Because as Steve says, when someone spends $150,000 or more on a new commercial boiler system, and after one heating season, it's not covered under warranty and it's failing, that's a much bigger issue than what the investment would have been up front on what you could do to better manage the water chemistry in that system.
Yeah, Brian, thank you. That's a great point. We're going to close on that one. So optimizing boiler chemistry, it's not an option anymore, and it can cost or save a lot of money if you maintain these systems. Steve, Brian, again, thank you so much for your time today, and everyone who joined us. We got to most all of the questions, so I'm happy about that. If there's anything else, you can reach out to me at dpicklyk@hpacmag.com, and I'll forward your questions on to the guys, and we'll get you some responses. This has been recorded, so this will be posted on our YouTube channel in the near future, and you'll be able to get to it through our website as well. Gentlemen, again, thank you very much, and thank you everyone for watching. Have a great Friday.
Thank you very much, everybody. Thanks, Doug.
Thanks, guys.